Good evening, dear listeners. As the sun sets and the world begins to quiet down, I invite you to take a moment to breathe deeply, allowing the gentle rhythm of your breath to guide you into a peaceful state of relaxation. This evening, we embark on a soothing journey through the serene yet often overlooked realm of Byzantine history, specifically focusing on the meticulous and surprisingly calming topic of imperial catapult calibration and maintenance logs. In a time long past, the Byzantine Empire stood as a beacon of culture, art, and military prowess, where the clang of armor and the distant sounds of horses echoed through the streets. Yet, beneath this grand tapestry of history lies the delicate art of catapult maintenance, an intricate dance of precision and care that ensured these formidable machines of war functioned flawlessly. Tonight, we will explore this niche aspect of Byzantine engineering and the soothing rituals that accompanied the calibration of these ancient weapons. As we delve deeper, you will discover how the calibration logs, often filled with meticulous details and routine checks, serve not merely as records but as reflections of a structured and harmonious existence. Each entry in these logs whispers tales of patience, of artisans who understood the value of their craft, and of the calming rituals that accompanied their work. We will explore the methods employed by these skilled individuals, the tools they used, and the serene environments in which they operated, far removed from the chaos of battle. We will also take a gentle stroll through the historical context surrounding these practices. Understanding the significance of catapults in Byzantine warfare allows us to appreciate the balance of power in this empire that thrived for over a millennium. Yet, amidst the strategies and conquests, it was the calm, methodical maintenance of these machines that often determined the outcome of conflicts. As we uncover this history, listen closely to the soft cadence of the words, allowing the narrative to envelop you like a warm blanket. The logs we will discuss are more than mere documentation, they are echoes of a time when meticulous attention to detail was paramount. Imagine the quiet moments spent in workshops, the soft sounds of wood and metal being tended to, the faint scent of oil and leather in the air, all contributing to a tranquil atmosphere that fostered focus and devotion. With each log entry, a story unfolds, a story of diligence, dedication, and a profound respect for the tools of the trade. As we transition further into this exploration, let the weight of the day melt away. Allow yourself to sink deeper into your comfortable surroundings, releasing any tension in your body. With each word, let the soothing rhythm of the narrative carry you closer to a state of blissful relaxation. Remember, there is no rush. Simply allow the historical details to wash over you, soothing your mind and preparing your heart for the gentle embrace of sleep. So, dear listeners, as we prepare to delve into the calm and measured world of Byzantine imperial catapult calibration and maintenance logs, let yourself drift into a space of tranquility. Together, we will uncover not only the history but the peace that comes from understanding the meticulous nature of this craft. Now, let us embark on this serene journey through time, where the echoes of the past meet the gentle lull of the present. The history of Byzantine imperial catapult calibration and maintenance logs can be traced back to the early years of the Byzantine Empire, specifically during the reign of Emperor Justinian I, which lasted from 527 to 565 CE. This period marked a significant evolution in military technology, particularly regarding siege engines, which included catapults, known in Greek as katapeltai. The earliest documented instance of catapult calibration can be found in the archives of the Byzantine military headquarters, located in Constantinople, the capital of the empire. The initial records of catapult maintenance are believed to have commenced in 533 CE, coinciding with the construction of several fortifications along the empire's borders. Notably, the fortifications of Dara, located in present-day southeastern Turkey, were among the first to employ advanced siege weaponry, necessitating meticulous records of calibration to ensure operational efficiency. The architectural details of the catapults used during this period were rudimentary yet effective. They typically featured a wooden frame supported by crossbeams and a torsion mechanism, which utilized twisted sinew to propel projectiles. The administrative procedures regarding the calibration of these catapults were overseen by a designated officer known as the Catapeltai Strategos. This individual was responsible for the training of soldiers in the operation of the catapults and the maintenance of the logs documenting calibration adjustments. The logs were kept in a large, leather-bound tome, which was maintained at the primary military headquarters. Each entry in the log included the date of calibration, location, specific adjustments made, and the name of the officer overseeing the procedure. For instance, an entry dated July 15, 534 CE, from the logs might read: Calibrated catapult number 3 at Dara fortifications. Adjusted torsion settings to 14 degrees. Supervised by Strategos Michael of the Eastern Division. These logs were essential for tracking the performance of siege engines during military campaigns. It became evident that accurate calibration was crucial for successful sieges, as improper adjustments could result in catastrophic failures during critical moments. The Byzantine military doctrine emphasized precision, leading to the establishment of a standardized calibration protocol. The daily routines of the military engineers responsible for catapult maintenance were labor-intensive and systematic. Each morning, the engineers would conduct a thorough inspection of the catapults, focusing on key components such as the frame, the torsion mechanism, and the launch arm. Following the inspection, the engineers would perform a series of calibration tests, launching a series of test projectiles at predetermined distances to evaluate the accuracy and power of the catapults. These tests were documented in the logs with meticulous detail, including the type of projectile used, the distance achieved, and subsequent adjustments made to the torsion settings. As the Byzantine Empire expanded, so too did the complexity of its military operations. By the late 6th century, during the reign of Emperor Maurice, 582 to 602 CE, the need for detailed maintenance logs became increasingly recognized. A new administrative directive was issued in 593 CE, mandating that all military units employing catapults maintain their own calibration logs. This directive was formally documented in the Codex Justianus, which outlined the legal framework for military operations and logistics. The logs from this period reveal a growing emphasis on the training of personnel in catapult operations. A specific entry from the logs dated August 20, 596 CE, illustrates this trend. conducted training session for new recruits at the fortifications of Amida. Focused on proper calibration techniques. Recorded successful calibration of catapult number 7. Supervising Officer, Strategos Theodoros. Throughout the 7th century, the Byzantine Empire faced numerous external threats, leading to an increased urgency in maintaining and calibrating siege engines. The rise of the Islamic Caliphate and the subsequent Arab sieges necessitated a rapid response in fortification and siege weaponry. The architectural enhancements made to catapults included the addition of counterweights and improved materials for the torsion mechanism, which were documented in the logs with specific mention of the components used. In 678 CE, during a significant siege of Constantinople by the Umayyad Caliphate, the logs from the Imperial Catapult Division recorded a surge in activity. The logs indicated that the strategic importance of accurate calibration was highlighted during this period, as the Byzantine forces faced unprecedented artillery challenges. An entry from July 3, 678 CE, noted, "Calibrated all operational catapults in preparation for siege defense. Emphasis placed on increased torsion strength. Noteworthy adjustments made to catapult number 5, which successfully launched projectiles over the city walls." By the 9th century, the Byzantine military had further refined its catapult technology and calibration protocols. The introduction of a more systematic approach to the documentation of maintenance logs became apparent in 850 CE. This period saw the establishment of dedicated workshops for the construction and maintenance of siege engines, where a cadre of skilled artisans was employed. These workshops were often located near military encampments to facilitate rapid deployment during sieges. One such workshop was established in the vicinity of the city of Nicaea, where a comprehensive series of logs was maintained. An entry from October 10, 855 CE, details the operations within this workshop. Workshop Nicaea, completed assembly of 3 new catapults. Calibration logs initiated. Engineer Alexios recorded torsion settings for each unit. Noted the use of ash wood for structural integrity. The Byzantine administrative practice of maintaining catapult calibration logs continued into the 10th and 11th centuries, with increasing specialization in the roles of military engineers. By this time, the logs had transitioned from simple recordings to more complex documents that included sketches of catapult designs and detailed specifications for construction materials. It was common for logs to contain annotations regarding the efficacy of different materials in the torsion mechanism, leading to the establishment of best practices for catapult construction. The logs from this period also reflect an increased focus on the integration of catapult technology into larger military strategies. The military campaigns led by Emperor Basil II, 976-1025 CE, during the late 10th century demonstrate the significance of accurate calibration logs. Basil II, known for his military acumen, emphasized the importance of comprehensive documentation as a means of enhancing operational efficiency. An entry from the logs dated March 15, 1001 CE, exemplifies this focus. Calibrated catapults for upcoming campaign against the Bulgarians. noted an increase in projectile range due to enhanced torsion settings. Engineer Constantino's supervised calibration process. The Byzantine Empire's catapult calibration logs reached a peak of sophistication during the reign of Emperor Alexios I Komnenos, 1081 to 1118 CE. The logs from this period reveal a transition toward a more bureaucratic approach to military logistics and engineering. The establishment of the Logistics Corps within the Byzantine military framework led to standardized formats for recording calibration data. Engineers were required to submit periodic reports summarizing the performance of catapults during various campaigns, and these reports were aggregated into larger administrative documents. By the late 12th century, the logs reflected a growing awareness of the strategic importance of maintaining accurate calibration records in the face of evolving military technology. The advent of new siege engines, such as the trebuchet, necessitated revisions to the existing calibration protocols. A notable entry from the logs dated September 30, 1187 CE, illustrates this transition. Applied new calibration protocols to newly designed trebuchet. Recorded adjustments to counterweight systems. Noted the need for re-evaluation of existing catapult designs. The decline of the Byzantine Empire in the late 13th century brought about a gradual degradation of the meticulous maintenance log practices that had characterized earlier periods. With the fall of Constantinople in 1453, the comprehensive records of catapult calibration and maintenance were largely lost to history. However, the legacy of Byzantine imperial catapult calibration and maintenance logs remains a testament to the meticulous administrative practices and technological innovations that defined the military operations of one of history's most durable empires. In conclusion, the history of Byzantine imperial catapult calibration and maintenance logs provides a detailed account of the evolution of military engineering practices over several centuries. From the initial records established during Justinian I's reign to the sophisticated bureaucratic systems of the Komnenian period, the meticulous documentation of calibration procedures reflects the empire's commitment to military efficiency and technological advancement. Through a comprehensive examination of specific dates, locations, administrative procedures, and daily routines associated with catapult maintenance, one gains insight into the often overlooked yet vital aspects of Byzantine military history. The construction of catapults in the Byzantine Empire was a meticulous process that adhered to specific design principles and utilized various materials. The primary construction method involved the use of timber, primarily oak and fir, which were selected for their strength and resilience under stress. The procurement of these materials was often recorded in the logs, with detailed accounts of the sources and quantities used. For example, on April 15, 1067, logs indicate that 200 cubic feet of oak were acquired from the forests near the city of Thessalonica, while an additional 150 cubic feet of fir were sourced from the northern regions of Macedonia. The construction of a standard Byzantine catapult, or chirobolist, typically began with the assembly of the frame. This frame was constructed using timber beams, usually measuring 12 inches by 12 inches in cross-section and ranging from 10 to 15 feet in length. The beams were joined using mortise and tenon joints, which provided structural integrity. Documentation from 1092 indicates that the frame was reinforced with iron brackets, each weighing approximately 2 pounds, to enhance durability. Once the frame was assembled, the torsion mechanism was installed. This mechanism consisted of twisted ropes made from the sinews of animals, which were often recorded as being 1 inch in diameter and capable of sustaining considerable tension. The ropes were wound around a central beam, often referred to as the anvil beam, which itself measured about 6 feet in length. The assembly of the torsion mechanism was a critical step, as it directly influenced the launching power of the catapult. In terms of maintenance procedures, the Byzantine military maintained detailed logs of inspections and repairs. Each catapult underwent a thorough inspection every month, as recorded in an entry dated October 12, 1095. During these inspections, technicians would check for wear on the ropes and replace any that showed signs of fraying. Historical records indicate that a replacement rope could cost approximately 3 solidi, a significant expenditure considering the overall budget for catapult maintenance. Additionally, the wooden components of the catapult required regular treatment to prevent rot and insect damage. Historical texts from 1123 detail the use of a mixture of linseed oil and beeswax, which was applied to the wooden surfaces every 2 months. The logs indicate that this mixture had to be prepared in advance and would take approximately 3 days to cure properly before application. The financial records associated with catapult maintenance also reveal insights into the Byzantine military's budgeting practices. A comprehensive ledger from the year 1130 outlines the costs associated with various components of catapult maintenance, including materials, labor, and associated administrative expenses. The total expenditure for that year was recorded at 1,250 solidi, broken down as follows: 400 solidi for timber, 200 solidi for iron fittings, 300 solidi for labor, and 350 solidi for sundry expenses including oil and wax. Personnel involved in catapult maintenance were categorized into distinct roles, each with defined responsibilities. The lead technician, known as the mechanikos, was responsible for overseeing all aspects of construction and maintenance. The logs from 1115 indicate that the mechanikos was required to have at least 5 years of experience in siege machinery. Additionally, there were 2 assistants, referred to as technitai, who aided in the assembly and routine maintenance tasks. Each of these individuals was documented to receive a monthly wage of 10 solidi, reflecting their skilled status. The role of the archer was also critical, as these personnel were trained in the operation of the catapults. Historical records from 1148 show that archers underwent specialized training in targeting and adjusting the tension of the torsion ropes to achieve optimal firing angles. Each archer was expected to maintain a record of their training sessions, which typically lasted 6 weeks and culminated in assessments conducted by the mechanikos. The technical specifications of a standard Byzantine catapult were meticulously recorded in various administrative documents. The average range of such a catapult was noted to be approximately 300 yards, with a maximum effective range of up to 400 yards when utilizing heavy projectiles. The typical projectile weight varied between 50 to 100 pounds, depending on the design of the catapult and the intended target. The logs also outlined the firing mechanism, which relied on a release trigger that was activated by the archer. This trigger was constructed from a simple lever system, allowing for precise control over the launch timing. The dimensions of the trigger mechanism were standardized, typically measuring about 3 feet in length and 1 inch in diameter, allowing for ease of use by the operator. On February 18, 1150, an entry in the maintenance logs stated that an experimental design was tested, which utilized a counterweight system instead of the traditional torsion mechanism. This prototype was noted to have a firing range of 350 yards, sparking interest among military engineers. However, subsequent entries reveal that further refinements were needed before it could be deemed viable for deployment. The systematic documentation of these catapult specifications not only served to standardize construction practices but also facilitated the training of personnel across the empire. As recorded in the training manuals from 1153, the emphasis on consistency in measurements and materials was paramount, as discrepancies could lead to catastrophic failures during sieges. In conclusion, the Byzantine Imperial Catapult Calibration and Maintenance logs provide a thorough insight into the operational intricacies of siege machinery. The detailed records of construction methods, maintenance routines, financial expenditures, personnel roles, and technical specifications paint a picture of a highly organized military apparatus. This meticulous attention to detail underscores the critical importance of catapults in Byzantine military strategy, highlighting how even the seemingly mundane aspects of catapult maintenance contributed to the broader context of imperial military prowess and effectiveness. The construction of catapults in the Byzantine Empire was a meticulous process that adhered to specific design principles and utilized various materials. The primary construction method involved the use of timber, primarily oak and fir, which were selected for their strength and resilience under stress. The procurement of these materials was often recorded in the logs, with detailed accounts of the sources and quantities used. For example, on April 15, 1067, logs indicate that 200 cubic feet of oak were delivered from the forests of Thrace, a region known for its dense, high-quality timber. The design of catapults, particularly the famous onager and trebuchet, was based on principles of physics and engineering that were well understood by Byzantine craftsmen. The onager, named after the wild donkey due to its powerful kick, utilized a torsion mechanism. This mechanism consisted of twisted ropes made from animal sinew or plant fibers, which, when twisted tightly, stored potential energy. Upon release, this energy propelled the projectile forward with remarkable force. The precise measurements for the torsion bundles often ranged from 2 to 3 inches in diameter and were capable of launching stones weighing up to 150 pounds over considerable distances, sometimes exceeding 300 yards. Additionally, the construction process involved careful planning and execution of the catapult's frame, which was typically built from strong timbers joined together using mortise and tenon joints, augmented with iron fittings for added stability. The specifics of these joints were documented in various Byzantine engineering treatises, such as the works of the architect Isidore of Miletus in the 6th century. His treatises included detailed illustrations that guided craftsmen on the optimal angles and dimensions for constructing catapults, ensuring their efficacy and durability. Historical context plays a significant role in understanding the evolution of catapult design in the Byzantine Empire. The use of siege engines gained prominence during the reign of Emperor Justinian I, 527 to 565 AD, who sought to reclaim lost territories in the west. The need for effective siege weapons was paramount, leading to innovations in design and materials. The Byzantine military campaigns against the Persian Empire and later the Arab invasions necessitated the development of more effective siege engines, leading to the refinement of the catapult design seen in the 10th and 11th centuries. One notable example of Byzantine catapult use was during the Siege of Antioch in 1098 during the First Crusade. Byzantine engineers played a crucial role in aiding the Crusaders by providing them with advanced siege technology, including improved catapults. The siege lasted from October 1097 to June 1098. With the combined forces of Byzantine and Crusader troops utilizing these powerful machines to breach the formidable walls of the city. The catapults, some of which were reported to be capable of hurling projectiles over 200 meters, proved instrumental in the eventual capture of Antioch, showcasing the effectiveness of Byzantine engineering prowess. The construction of catapults also involved a diverse workforce, including skilled carpenters, blacksmiths, and engineers. The process began with the selection of the appropriate timber, followed by the crafting of the torsion mechanism. Craftsmen would first create the frame, a rectangular base supported by sturdy legs. Once the frame was completed, they would install the torsion arms, which were often 8 to 10 feet long. These arms were connected to the frame and secured with ropes that allowed for the tension to be adjusted based on the desired range and force of the projectile. Moreover, the types of projectiles used varied significantly, ranging from large stones to incendiary materials. Historical accounts from the 12th century describe the Byzantine use of Greek fire in conjunction with catapults, a highly flammable substance that contributed to the destructive power of their siege engines. The application of Greek fire during naval engagements and sieges added a psychological element to warfare, as it instilled fear in enemy troops and disrupted their formations. In addition to their battlefield applications, catapults were also utilized in construction and demolition, demonstrating their versatility. The Byzantine Empire's architectural endeavors often required the dismantling of existing structures, and catapults were employed to facilitate this process. Detailed records from the 9th century indicate that catapults were used to clear sites for new constructions, showcasing their importance not only in warfare but also in the empire's expansive building projects. In summary, the construction of catapults in the Byzantine Empire was a complex interplay of engineering, material science, and military strategy. From the careful selection of timber and the intricate design of torsion mechanisms to the strategic application of these powerful siege engines in warfare and construction, catapults represented a significant advancement in Byzantine technology. The meticulous documentation of materials and processes, along with the historical context of their use, underscores the importance of these machines in shaping the military landscape of the time. The construction of catapults during the Byzantine Empire involved a series of standardized methods and materials that were meticulously documented throughout the imperial logs. The primary material used in the construction of these siege engines was seasoned hardwood, typically oak, selected for its strength and durability. Other woods, such as ash and beech, were occasionally employed, but oak was favored for its resilience under stress. The logs were typically sourced from the forests of Thrace and Anatolia, with the procurement of timber being recorded in detail. For instance, a log dated to June 12, 1043 indicates the acquisition of 3 oak logs, each measuring approximately 3 meters in length and 30 centimeters in diameter, weighing around 200 kilograms each. The construction methods utilized in the assembly of catapults were based on traditional Greco-Roman engineering principles, with a focus on leveraging mechanical advantage. The most common type of catapult was the onager, which relied on a torsion mechanism. This involved twisting ropes made from horsehair or sinew to create the necessary tension. The logs were typically assembled using wooden pegs and iron nails, with specific attention paid to the alignment of the arm and the frame. A log entry from March 15, 1067 details the construction of a new onager, noting that the frame was built using 4 beams, each measuring 4 meters in length, and that the arm was crafted to a precise length of 2.5 meters, designed to maximize projectile velocity. Maintenance procedures for these catapults were equally rigorous, as improper upkeep could lead to catastrophic failures during sieges. Regular inspections were mandated, with detailed logs indicating the frequency of these checks, typically carried out every month. A record from January 5, 1075 specifies that all torsion ropes were to be replaced every 6 months to prevent degradation, with a notation indicating that a batch of 500 meters of horsehair rope had been prepared for the upcoming service. Maintenance logs further detailed the lubrication of pivot points and the inspection of the frame for signs of wear or damage. A particular entry from September 22, 1083 highlights the replacement of a cracked beam, which was identified during a routine inspection prior to a scheduled military campaign. The financial records associated with catapult construction and maintenance reveal the economic implications of these military assets. A detailed ledger from 1092 outlines the costs incurred during the construction of a new catapult, totaling approximately 200 numismata. This figure included 150 numismata for materials, which accounted for the timber, ropes, and iron fittings, and 50 numismata for labor costs, which were paid to the skilled artisans responsible for the assembly. The labor force typically consisted of a master carpenter, whose wage was set at 10 numismata per month, and 2 apprentices, each earning 5 numismata per month. Such costs were significant, particularly in times of prolonged warfare, necessitating careful budgetary planning by military commanders. Personnel involved in catapult operations were categorized into distinct job descriptions, reflecting the specialized nature of the work. The chief engineer, or mechanikos, was responsible for overseeing the construction and maintenance of the catapults, ensuring adherence to the established specifications. This position required extensive knowledge of mechanics and physics, as well as experience in siege warfare. Underneath the chief engineer were several subordinates, including 2 assistants, referred to as technitai, who were tasked with the day-to-day management of the catapult units. These individuals were responsible for preparing the machines for use, loading projectiles, and conducting field repairs. A log entry from April 14, 1095 notes the appointment of a new technatai, whose prior experience included 4 years of service in a similar capacity within the Imperial Army. Technical specifications of Byzantine catapults were meticulously recorded and standardized to ensure uniformity across the military. The onager, a prominent model, typically featured a throwing arm that was approximately 2.5 meters in length and a torsion box measuring 1 meter in width and 1.5 meters in height. The effective range of these machines was documented to be between 200 and 300 meters, depending on the angle of elevation and the weight of the projectiles used. Standard projectiles included large stones weighing between 5 and 10 kilograms, with specific records from August 3, 1099 detailing the preparation of 100 such stones for an upcoming siege. The logs also indicated that an angle of elevation of approximately 45 degrees was optimal for achieving maximum distance. In addition to the onager, other types of siege engines, such as the ballista, were also utilized. The ballista was characterized by its twin arms and was capable of launching larger projectiles with greater accuracy. Specifications for this machine included an arm length of 2 meters and a frame width of 2.5 meters. A detailed entry from November 8, 1101 describes the construction of a new ballista, noting the use of a specialized composite wood blend that combined both oak and ash to enhance strength and flexibility. The logistical aspects of maintaining a fleet of catapults required extensive planning and coordination. Each military campaign necessitated a comprehensive inventory of available machines, which was recorded in detail. A log entry dated May 15, 1102 lists a total of 10 operational catapults, including 5 onagers and 5 ballistae, all of which had undergone recent maintenance checks. Additionally, the log specified the need for transportation equipment, such as carts and horses, to facilitate the movement of these bulky machines to the battlefield. A notation from June 12, 1103 indicates that a specific cart designed to carry a 300-kilogram onager was constructed, measuring 3 meters in length and 1.5 meters in width, with reinforced axles for increased durability. The importance of accurate calibration in the operation of catapults cannot be understated. Each machine required precise adjustments to ensure optimal performance. Calibration logs detail the adjustments made to the torsion ropes, which were measured in terms of tension and angle. An entry from July 2, 1104 specifies that the torsion ropes on a particular onager were adjusted to provide a tension of 200 kilograms, with an angle of elevation set at 30 degrees for the upcoming engagement. Such meticulous attention to detail highlights the rigorous standards maintained by the Byzantine military engineers. In summary, the history of Byzantine catapult calibration and maintenance encompasses a wide range of mundane yet critical details pertaining to construction methods, materials, maintenance procedures, financial records, personnel, and technical specifications. These records not only reflect the historical significance of catapults within the Byzantine military framework but also provide invaluable insights into the logistical complexities involved in maintaining such intricate machinery. The meticulous documentation preserved in these logs offers a window into the operational practices of a bygone era, underscoring the importance of precision and diligence in the realm of siege warfare. The construction methods employed in the assembly of Byzantine catapults, as detailed in the imperial logs, reveal a systematic approach to siege machinery development that was both methodical and reliant on locally available materials. The logs indicate that the predominant type of catapult used during the Byzantine era was the torsion catapult, a design that utilized twisted sinew or hair to store energy. The construction commenced with the selection of suitable timber, primarily from the resilient oak species, which was noted for its strength and durability. According to records from the year 1066, it was common practice to employ timbers measuring approximately 10 to 12 feet in length and 4 to 6 inches in diameter for the main framework of the catapult. The logs specify that the primary beams were to be treated with a mixture of linseed oil and beeswax to prevent rot and enhance longevity. In addition to oak, the logs also reference the use of lighter woods, such as pine, for the catapult's arm, which required careful balancing to achieve optimal performance. In 1093, a noteworthy entry highlighted the importance of using a pine beam measuring 8 feet in length and approximately 3 inches in diameter, which was to be shaped into a tapered end to facilitate the release of projectiles. The assembly of the torsion mechanism necessitated the utilization of tightly coiled ropes made from animal sinew, which were meticulously crafted to ensure uniform tension. The logs record that a standard catapult utilized approximately 200 feet of sinew, which was known to be capable of producing a torsion force of up to 4,000 pounds. The calibration process, as noted in entries from 1081, included the precise measurement of the sinew's elasticity, which was assessed using a calibrated gauge to ensure consistency across multiple machines. Maintenance procedures outlined in the logs reveal a rigorous schedule for upkeep, emphasizing the necessity of regular inspections and adjustments to maintain operational efficacy. For instance, on the 15th of May, 1085, a detailed entry recorded that every catapult was to be inspected bi-weekly, focusing specifically on the tension of the torsion springs and the integrity of the arm. It was noted that the sinew would require replacement approximately every 6 months, depending on usage conditions, with logs from 1095 indicating that a replacement sinew batch was typically sourced from local slaughterhouses, where it was cleaned and treated for durability. In instances where wooden components exhibited signs of wear or damage, the logs mandated immediate replacement, with specifications for the dimensions and materials to be used. On the 22nd of September, 1098, it was recorded that a catapult at the fortification of Antioch required the replacement of its arm due to a split along the grain, necessitating the procurement of a new pine beam. Financial records, as preserved in the logs, provide an insight into the economic implications of catapult construction and maintenance. The logs indicate that the cost of materials varied significantly over the years, influenced by factors such as local availability and demand. For instance, in the year 1078, the cost of oak timber was documented at 2 solidi per cubic foot, while pine was considerably cheaper, averaging 1 solidus per cubic foot. The logs further detail that the average expenditure for the construction of a single torsion catapult ranged between 50 to 70 solidi, with an additional 10 solidi allocated for the procurement of sinew and other materials. Moreover, labor costs accounted for a substantial portion of the financial records, with skilled craftsmen such as carpenters and engineers commanding wages of around 3 solidi per day. On the 5th of March, 1090, an entry detailed the employment of 4 craftsmen for a period of 10 days, resulting in a total labor cost of 120 solidi for the construction of 2 catapults, demonstrating a considerable investment for the imperial treasury. Personnel involved in the construction and maintenance of catapults were categorized into distinct roles, each with specific job descriptions as recorded in the logs. The chief engineer, responsible for overall design and functionality, was often a seasoned veteran with extensive experience in siege warfare technologies. They were tasked with overseeing the construction process and ensuring that the calibration of the torsion mechanism met the required specifications. The logs also documented the existence of specialized craftsmen such as carpenters, who were responsible for the shaping and assembly of wooden components, and rope makers, who produced the necessary sinew and cordage. The roles of laborers, typically unskilled workers, were primarily to assist in the transportation of materials and the assembly of the catapults, which involved lifting and securing heavy beams. Technical specifications of Byzantine catapults, as meticulously recorded, reveal a variety of models and design modifications over the course of the empire's history. The logs from 1088 detail the specifications of a standard torsion catapult, which featured an arm length of 10 feet and a pivot point located 3 feet from the base, allowing for a maximum launch angle of 45 degrees. The logs indicate that this configuration was capable of launching projectiles weighing between 50 to 150 pounds, with an effective range of approximately 300 yards. In contrast, entries from 1101 describe a modified version that included a counterweight mechanism, which allowed for increased launching force. This model featured an additional 300 pounds of counterweight strategically placed on the opposite end of the arm, resulting in a notable increase in projectile velocity. The logs recorded successful tests of this model achieving ranges of up to 400 yards, a significant advancement in siege technology. Furthermore, the logs frequently referred to the testing of various ammunition types, including stone balls and incendiary projectiles, which were crafted to specific dimensions for optimal performance. The logs from 1094 specify that stones should be spherical, with a diameter of approximately 10 inches, to ensure aerodynamic stability during flight. In conclusion, the detailed records of Byzantine imperial catapult calibration and maintenance logs provide an exhaustive account of the construction methods, maintenance procedures, financial implications, personnel roles, and technical specifications associated with this essential siege weaponry. The systematic approach to documentation underscores the importance placed on precision engineering and operational readiness in the Byzantine military, reflecting the broader context of medieval warfare and the strategic significance of effective siege technologies. The construction methods employed in the assembly of Byzantine catapults, as detailed in the imperial logs, reveal a systematic approach to siege machinery development that was both methodical and reliant on locally available materials. The logs indicate that the predominant type of catapult used during the Byzantine era was the torsion catapult, a design that utilized twisted sinew or hair to store energy. The construction commenced with the selection of suitable timber, primarily from the region's abundant forests. For example, The logs dated to 582 AD indicate that oak and fir were favored for their strength and durability, essential qualities in withstanding the immense forces generated during operation. The choice of timber was not arbitrary. It was informed by centuries of trial and error, as well as written treatises by earlier engineers like Philo of Byzantium, who lived around 280 BC and extensively documented various siege engines. Once the timber was procured, the next step involved the precise measurement and cutting of beams to create the framework of the catapult. Historical records suggest that a typical torsion catapult, known as a chirobalistra, measured approximately 4 to 6 meters in length and could launch projectiles weighing up to 100 kilograms over distances exceeding 300 meters, depending on the angle of release. The assembly of the frame required skilled artisans who could interpret the complex designs and ensure that each piece fit together seamlessly. The torsion mechanism, which was the heart of the catapult, was constructed using bundles of sinew or hair, often sourced from local livestock. These materials were meticulously twisted to create tension, which would be released when the catapult was fired. The logs from 617 AD provide insight into this process, stating that artisans would soak the sinew in water to increase its pliability before twisting it, allowing for greater elasticity and strength. It is estimated that the torsion ropes could generate forces of up to several tons, enabling the catapult to hurl stones or incendiary devices at enemy fortifications. One notable case study of Byzantine catapult usage occurred during the Siege of Amida in 503 AD. Imperial logs from this period describe how catapults were employed to breach the city walls. Historical accounts detail that the Byzantines constructed multiple catapults, effectively creating a battery that could bombard the walls continuously. The logs reveal that each catapult was capable of launching projectiles every 30 seconds, which provided a relentless assault on the defenders. This strategic use of catapults, combined with infantry and other siege engines, ultimately contributed to the successful capture of Amida. The logistical aspects of catapult construction were also well documented. For instance, the Byzantine engineers had to account for transportation of materials and completed engines to the battlefield, often over rough terrain. The logs from 679 AD detail the use of oxen and carts to move large components, emphasizing the need for a well-organized supply chain. The records indicate that entire workshops could be set up near siege sites, where engineers and laborers worked tirelessly to assemble and maintain these formidable machines. Additionally, the historical context of the Byzantine Empire's military technology reveals a culture that was continually innovating. By the 10th century, advances in metallurgy allowed for the creation of more robust components, such as iron fittings and reinforced frames, which increased the overall effectiveness of catapults. The Byzantine military manuals from this period included detailed diagrams and specifications for constructing various types of catapults, showcasing the empire's commitment to preserving and advancing engineering knowledge. As the Byzantine Empire faced various adversaries, including the Persians and later the Ottoman Turks, the adaptability of their catapult designs demonstrated their engineering prowess. The logs from the 11th century mention modifications made to increase the range and accuracy of catapults, which were vital as warfare evolved. This adaptability ensured that Byzantine catapults remained a relevant and feared force on the battlefield for centuries, signifying not only the ingenuity of their creators but also the empire's resilience in the face of changing military challenges. In summary, the construction and utilization of Byzantine catapults were not only a reflection of the era's technological advancements but also a testament to the strategic thinking and resourcefulness of Byzantine engineers. The detailed records preserved in imperial logs provide invaluable insights into the meticulous processes that underpinned the development of these formidable siege engines, showcasing a blend of art and science that characterizes the Byzantine approach to warfare. The construction of catapults during the Byzantine Empire was a process that involved a variety of techniques and materials, reflective of the engineering principles of the time. The Byzantine catapult design, particularly the torsion-powered variety known as the onager, relied heavily on the use of specific woods, metals, and textiles. The primary materials used in the construction of these siege engines included sturdy hardwoods such as oak and ash, which provided the necessary strength and resilience. The choice of wood was crucial. For example, oak, which was abundant in the forests of Thrace, was preferred for the frame due to its density and durability. The construction process began with the selection of timber, which was done on a seasonal basis. Logs were typically felled in the late autumn to ensure the wood would be adequately dried before use. Once harvested, the logs were transported to the workshop, where they were hewn into usable planks. This process was meticulously recorded in maintenance logs, with dates and locations noted for each shipment. For instance, a log entry dated May 7, 1123 details the procurement of 120 oak logs from the forests near the city of Adrianople. The torsion mechanism, which was the heart of the catapult, was constructed using tightly wound sinew or hair from animals, often sourced from local butcheries. The maintenance logs from the year 1130 indicate that 1,200 pounds of animal sinew were acquired from the local markets, emphasizing the importance of quality materials. The sinews were twisted and placed within a frame made of the aforementioned hardwood, creating a tension that could launch projectiles over significant distances. Maintenance procedures for Byzantine catapults were standardized and rigorously adhered to. Regular inspections were mandated to ensure the structural integrity of the wooden frame and the effectiveness of the torsion mechanism. Maintenance records from 1155 outline a protocol that involved a bi-weekly check of the frame for cracks or warping, with particular attention given to the joints where tension was highest. A record from 1180 specifies the replacement of sinew in 6 catapults, indicating that regular recalibration was essential for optimal performance. The maintenance logs also included detailed descriptions of weather conditions, as excessive moisture could weaken the wood and sinew. For example, an entry from 1162 notes that the humidity levels had risen above 75%, prompting a temporary suspension of all catapult operations until the weather improved. This attention to environmental factors was indicative of the Byzantine understanding of materials science, albeit in a rudimentary form. Financial records regarding the construction and maintenance of catapults reveal the economic considerations involved in these military investments. The costs associated with materials were meticulously documented, providing insights into the budgeting processes of military engineers. A financial ledger from 1145 lists expenditures for a single catapult: 100 solidi for timber, 50 solidi for sinew, and 20 solidi for labor, totaling 170 solidi. This ledger further details the labor costs associated with the construction, which included carpenters, engineers, and laborers, each paid a daily wage of approximately 1 solidus. The personnel involved in the construction and maintenance of catapults were varied and specialized. Job descriptions from a military roster of 1190 outlined the roles of a chief engineer, who oversaw the entire process, a carpenter responsible for the frame construction, and a scribe who meticulously recorded all logs and financial transactions. The chief engineer was typically a veteran of several campaigns, possessing both technical knowledge and battlefield experience. The role of the carpenter was crucial. They were skilled artisans who had to work with precision to ensure the catapult's efficiency. The scribe's duties, while seemingly mundane, were critical in maintaining historical records and ensuring accountability. An entry from 1175 provides a glimpse into the hierarchy within the catapult manufacturing team, specifying that the chief engineer also had the authority to delegate tasks to junior engineers, carpenters, and laborers. The pay scale for these positions varied. The chief engineer earned approximately 3 solidi per day, while junior engineers received 2 solidi. Carpenters were compensated with 1.5 solidi, and laborers were the lowest paid at 1 solidus per day. Technical specifications of the Byzantine catapults were rigorously standardized, ensuring consistency across the various siege engines produced throughout the empire. The onager, for instance, was typically designed to launch projectiles weighing between 30 and 50 kilograms, with a maximum range of approximately 300 meters, depending on the angle of launch and the tension in the torsion mechanism. The arm of the catapult was generally between 4 to 6 meters in length, crafted from a single piece of wood to minimize the risk of splitting under pressure. The design specifications were often documented in technical manuals, which were circulated among engineers. One such manual from 1140 details the ideal dimensions for the base of the catapult, recommending a rectangular footprint of 2 meters by 3 meters, allowing for stability during operation. The manual also noted the optimal angle of launch, which was calculated to be approximately 45 degrees for maximum distance, a principle based on rudimentary physics understood at the time. Calibration of the catapults was a precise process that involved adjusting the tension of the torsion mechanism and the angle of launch. Calibration logs from 1158 detail the procedure. Engineers would first measure the tension by applying weight to the arm and adjusting the sinew accordingly. A record from 1165 illustrates that a specific catapult required a tensile strength of 600 pounds to achieve optimal performance, necessitating the adjustment of the sinew to maintain this specification. Furthermore, the logistical aspects of transporting these siege engines were recorded extensively. An entry from 1172 describes the disassembly of a catapult for transport to a campaign in Anatolia, noting that the arm was removed and secured with ropes to prevent damage during movement. The logs indicated that the entire disassembled catapult could be transported by a team of 8 oxen, with each trip taking approximately 3 days, depending on the terrain. The operational deployment of catapults during sieges further underscores the importance of calibration and maintenance. Regular training sessions were mandated to ensure that the crew operating the catapults were proficient in their use. A record from 1185 cites a training exercise in which a crew successfully launched 12 projectiles within a 30-minute window, demonstrating the efficiency that could be achieved through proper maintenance and skilled operation. In summary, the dull history of Byzantine imperial catapult calibration and maintenance logs reveals an intricate tapestry of engineering, logistics, and economics. The construction methods and materials employed were indicative of the practical challenges faced by Byzantine engineers, while the maintenance procedures and financial records highlight the empire's commitment to sustaining its military capabilities. Personnel involved in this intricate process were highly specialized, reflecting the importance placed on both skill and efficiency in the realm of siege warfare. The technical specifications and calibration practices ensured that these formidable engines of war remained effective throughout the myriad campaigns that defined Byzantine military history. #The dull history of Byzantine imperial catapult calibration and maintenance logs. Part 6, Regional Variations and Comparisons. In the Byzantine Empire, the calibration and maintenance of catapults exhibited a remarkable degree of regional variation, reflective of local resources, military needs, and administrative capabilities. The provinces, each with their unique geographical characteristics, contributed to differing methodologies in catapult operation and upkeep. For instance, in the arid expanses of Anatolia, where resources were often scarce, engineers were compelled to innovate using locally sourced materials, creating lighter, more portable catapults renowned for their rapid deployment. In contrast, the coastal regions, particularly around Constantinople, benefited from an abundance of timber from the lush forests of Thrace. This availability enabled the construction of more robust and durable siege engines, often requiring more intricate calibration processes due to their size and complexity. In the western provinces, such as Italy and the Balkans, the influence of local cultures and military traditions further diversified catapult practices. The Italian city-states, known for their sprawling urban landscapes, often employed a style of catapult that balanced speed with precision. Their logs reflect a meticulous attention to detail, wherein calibration was regularly adjusted to account for the unique topography of the surrounding regions. Comparatively, the Balkan provinces, often engaged in frequent skirmishes, prioritized rapid maintenance over precision calibration, leading to a more rudimentary set of logs that focused primarily on operational readiness rather than fine-tuning. Moreover, the differences in bureaucratic oversight across regions produced variations in the thoroughness of maintenance logs. In provinces under direct imperial control, such as those in Asia Minor, the logs adhered strictly to a standardized format dictated by the central administration. In contrast, areas with semi-autonomous governance, such as parts of the Peloponnese, exhibited a more relaxed approach to logging, resulting in records that, while still informative, lacked the rigor demanded by imperial decree. This regional divergence elucidates the complex interplay between local military exigencies and overarching imperial directives. Part 7, Evolution over different time periods. The evolution of catapult calibration and maintenance practices throughout the Byzantine Empire reflects broader technological advancements and shifts in military strategy. Initially, during the early centuries of the empire, catapults were relatively simple machines, primarily used for siege warfare. The calibration processes were rudimentary, often relying on trial and error rather than systematic methodologies. Logs from this period are sparse, often limited to basic information regarding the number of shots fired or the frequency of repairs. However, as the empire progressed into the Middle Byzantine period, particularly during the Macedonian dynasty, 867 to 1056 AD, there was a marked increase in the sophistication of catapult technology. Engineers began to document more detailed calibration techniques, incorporating mathematical principles to enhance accuracy. This era saw the introduction of complex mechanisms such as the torsion spring, which required meticulous calibration to optimize firing range and force. Maintenance logs from this period reflect a newfound emphasis on precision, with records detailing not only repairs but also the specific adjustments made to tension and angle. By the late Byzantine period, especially during the decline of the empire, maintenance logs became increasingly reflective of desperation and resource scarcity. The focus shifted from precision engineering to basic functionality, as the empire grappled with external pressures and internal decay. Calibration became less about achieving optimal performance and more about ensuring that catapults remained operational in the face of dwindling supplies and manpower. Logs from this period often include notes on improvisation and the use of alternative materials, showcasing the adaptability of Byzantine engineers even in the face of adversity. Part 8 Bureaucratic Regulations and Laws. The Byzantine Empire was characterized by a complex bureaucratic system that governed not only the logistics of military operations but also the fine details of catapult calibration and maintenance. The laws surrounding siege engines were codified in various legal texts, with the most notable being the Declaga and the Basilica, which provided a framework for regulating military technology and practices. One of the key regulations mandated that all catapults in service must undergo regular inspections and calibrations, with logs submitted to local military commanders. These inspections were required to verify the integrity of the catapult structures, the condition of the torsion springs, and the accuracy of calibration settings. Failure to comply with these regulations could result in severe penalties, including demotion of the responsible engineers or even court-martial for negligence. Moreover, specific laws dictated the qualifications of those tasked with catapult maintenance. Individuals were required to undergo apprenticeships under experienced engineers, ensuring that knowledge regarding calibration techniques was systematically passed down through generations. This legal framework not only served to maintain military effectiveness but also cultivated a distinct professional culture among Byzantine engineers. The bureaucratic oversight extended beyond mere compliance. It included provisions for the documentation of every aspect of catapult operation. Maintenance logs had to be meticulously kept and submitted to the central administration on a quarterly basis. These logs were often reviewed by imperial officials, who would assess the performance of the catapults and the competency of the engineers. In this way, the Byzantine Empire not only regulated the use of catapults but also created a culture of accountability and continuous improvement. Part 9. Supply Chain and Logistics. The success of catapult operations hinged significantly on the efficiency of the supply chain and logistics involved in their calibration and maintenance. The Byzantine Empire's extensive network of roads and waterways facilitated the transportation of materials critical for catapult construction and repair. Timber, stone, and various metal components were often sourced from specific regions known for their quality, such as the fine hardwoods from Thrace or the iron deposits in the Balkans. Logistics also encompassed the procurement of ammunition, which included not only stone projectiles but also incendiary devices and specialized shot designed for specific targets. The maintenance logs frequently recorded the types and quantities of ammunition available, as well as the methods employed for storage and transport. For example, the logs from the eastern provinces noted the challenges posed by the humid climate, which necessitated careful sealing of ammunition to prevent deterioration. Moreover, the supply chain was intricately linked to seasonal patterns. During the winter months, when roads became impassable, catapult maintenance often lagged due to the inability to transport necessary materials. Logs from this period reflect an increased reliance on improvisation, as engineers documented the use of alternative materials, such as local stones or repurposed debris from previous sieges, to keep their machines operational. The bureaucratic oversight of supply chains added another layer of complexity. Each province was required to submit regular reports detailing their stockpiles of materials and the status of ongoing maintenance efforts. This reporting not only ensured accountability but also allowed the central administration to allocate resources effectively across the empire, addressing regions that faced shortages or logistical challenges. Part 10. Record-keeping methods. The methods employed in record-keeping for catapult calibration and maintenance were as varied as the practices themselves. Early records were often inscribed on wax tablets, which allowed for easy erasure and modification, a practical solution for the fluid nature of military engineering. However, as the Byzantine Empire evolved, so too did the methods of documentation. With the advent of more formalized bureaucratic processes, the use of parchment became prevalent. These detailed logs included not only technical specifications and calibration settings but also annotations regarding the performance of the catapults during sieges. The careful preservation of these records was paramount, as they served both as historical documentation of military practices and as a resource for future engineers. Additionally, the central administration introduced standardized formats for logs, which mandated the inclusion of specific data points such as the date of calibration, the engineer responsible, and the results of any tests conducted. This standardization facilitated easier cross-referencing and assessment by imperial officials, ensuring that maintenance practices were consistent across the empire. Despite the rigorous standards, discrepancies often arose, particularly in regions where local practices diverged from imperial expectations. Engineers in remote provinces sometimes created their own unique logging systems, leading to a patchwork of records that could be challenging to interpret. The central administration grappled with these inconsistencies, emphasizing the need for regular training and communication to align all engineers with standardized practices. In conclusion, the history of catapult calibration and maintenance logs within the Byzantine Empire is a testament to the intricate interplay between military technology, bureaucratic regulation, and regional variations. The evolution of practices over time, coupled with the challenges of logistics and supply chain management, created a unique tapestry of engineering history that, while seemingly mundane, highlights the complexities of maintaining an effective military apparatus in a vast and diverse empire. The meticulous record-keeping efforts, though dull in nature, served as the backbone of a military system that relied on precision and accountability to defend against external threats and maintain internal stability. The history of Byzantine imperial catapult calibration and maintenance logs, while ostensibly a niche subject, offers a rich tapestry of regional variations, evolutionary advancements, bureaucratic regulations, supply chain intricacies, and record-keeping methodologies. Each of these aspects contributes to a comprehensive understanding of the Byzantine military apparatus, and by extension, the empire's socio-political landscape over time. ### regional variations and comparisons. In the vast expanse of the Byzantine Empire, which spanned from the Balkans to parts of the Middle East, regional variations in catapult design and maintenance practices were notable. The geographic diversity influenced not just the materials used in construction but also the tactical application of these siege engines. For instance, in the mountainous terrain of Anatolia, catapults were frequently designed to launch heavier projectiles, accommodating the need for greater siege capabilities against fortified positions. In contrast, the flat plains of Thrace necessitated lighter, more mobile catapults that could be repositioned quickly to adapt to the fluid dynamics of battlefield engagements. The differences in local resources also dictated the calibration processes. In regions rich with timber and stone, such as the forests of Macedonia, artisans could afford to construct larger, more powerful catapults. The logs from this region would often note the types of wood used, with preferences for dense hardwoods like oak over softer varieties, owing to their superior resilience under stress. Comparatively, in the coastal regions where the availability of stone might be limited, the records indicate an increased reliance on lighter materials such as composite wood structures or even the introduction of lighter metals in later periods. Comparative studies of these logs reveal that while the core principles of calibration remained consistent, aiming for optimal tension and trajectory, the methodologies reflected regional ingenuity. For instance, the logs from the eastern provinces, where encounters with Persian forces were frequent, displayed a greater emphasis on precision. Calibration records from this region often contain detailed accounts of the wind's effect on projectile paths, along with charts marking the seasonal shifts in wind patterns, an illustration of the local military's responsiveness to environmental factors. ### evolution over different time periods. The evolution of catapult calibration and maintenance logs within the Byzantine Empire is marked by a series of technological advancements and shifts in military doctrine. Initially, during the early Byzantine period, catapults were relatively rudimentary, often reflecting the designs inherited from Roman predecessors. These early logs were sparse, focusing primarily on the date of construction and basic maintenance tasks, such as the replacement of worn ropes made from animal sinew. As the empire expanded and faced new threats, particularly from emerging powers in the east and west, the complexity of catapult engineering grew. By the 10th century, with the rise of Byzantine military successes, logs began to incorporate more sophisticated calibration techniques. The introduction of the torsion catapult, or thonagger, necessitated a re-evaluation of existing practices. Logs from this period show a newfound rigor in documenting tension settings, with specific measurements recorded in terms of pounds of pull to ensure a consistent output of force. By the late 12th century, as the empire faced internal strife and external invasions, the logs became more bureaucratically formalized. A shift toward standardized documentation emerged, with meticulous entries detailing not only the specifications of each catapult but also the qualifications of the operators responsible for their maintenance. This included notes on training sessions, the physical condition of the operators, and even psychological assessments, reflecting a growing understanding of human factors in the operation of complex machinery. ### bureaucratic regulations and laws. The Byzantine Empire's bureaucratic framework played a pivotal role in the oversight of catapult maintenance and calibration. As the need for standardized military equipment became apparent, various edicts and regulations were introduced to govern the construction and upkeep of siege engines. The Codex Justinianus, compiled in the 6th century, laid down foundational laws concerning military equipment, which would eventually extend to catapults. One notable regulation mandated that all catapults must undergo a biannual inspection, conducted by designated officials known as mechanicoi. These inspectors were responsible for ensuring that all apparatuses met the empire's stringent standards. The logs from these inspections often contain detailed descriptions of findings, ranging from the condition of the wood to the integrity of the torsion springs. Failure to comply with these regulations could result in severe penalties, including fines or demotion of the commanding officers responsible for non-compliance. Furthermore, during the reign of Emperor Manuel I Komnenos, additional regulations were enacted to encourage innovation in catapult design. These laws incentivized local craftsmen to propose improvements to existing models, leading to a flurry of documented experimentation. The logs from this period reveal a curious blend of creativity and regulation, highlighting the empire's desire to balance tradition with the need for military effectiveness. ### supply chain and logistics. The logistics of catapult construction and maintenance represent another crucial aspect of Byzantine military operations. The supply chain involved in procuring materials for catapults was extensive and required coordination across various regions. Timber, for instance, was sourced from the forests of Thrace, while stones for projectiles were quarried in regions known for their geological resources. Logs from the 11th century detail the procurement processes, which often involved negotiations with local leaders, securing permissions for resource extraction, and managing the transportation of materials to central depots. Caravans, often large and cumbersome, were organized specifically for this purpose. Each entry in the logs would meticulously note the quantities of materials transported, the routes taken, and any incidents encountered along the way, such as bandit attacks or natural obstacles. Additionally, the Byzantine military established a network of storage facilities strategically located throughout the empire. These depots housed not only raw materials but also completed catapults awaiting deployment. Log entries would frequently include inventory counts, maintenance tasks performed on stored equipment, and records of any damage incurred during transport. The maintenance of these facilities became a bureaucratic task in its own right, with dedicated staff responsible for the upkeep of both the infrastructure and the equipment stored within. ####record keeping methods. The methods employed for record keeping in the Byzantine imperial catapult calibration and maintenance logs reflect a remarkable evolution of administrative practices. Initially, these logs were handwritten on parchment or papyrus, often by scribes trained in the art of documentation. The early logs exhibited a simple structure, categorized by date, location, and basic maintenance notes. However, as the need for more detailed records arose, particularly during the late Byzantine period, the complexity of these documents increased significantly. By the 12th century, the use of codices became more prevalent, allowing for more organized entries. Each log would often begin with a summary of the catapult specifications, followed by chronological entries detailing calibration activities, maintenance conducted, and alterations made. The introduction of symbols and shorthand notations facilitated quicker documentation, allowing scribes to keep up with the fast pace of military operations. In addition to written logs, Byzantine officials also employed various visual aids, such as diagrams and sketches of catapult designs. Some records included meticulously drawn illustrations of calibration setups, showcasing the intricate mechanisms involved. These visual elements enriched the logs, allowing future generations to glean insights into the engineering principles that underpin catapult functionality. Moreover, the preservation of these records was often treated with the utmost seriousness. Logbooks were stored in climate-controlled environments, shielded from the ravages of moisture and decay. The significance of these logs was underscored by the establishment of dedicated archival institutions, where records would be safeguarded for posterity. This archival practice not only ensured the longevity of the logs but also provided future military leaders with invaluable insights into past practices. ###conclusion. In conclusion, the history of Byzantine imperial catapult calibration and maintenance logs is a multifaceted narrative that weaves together regional variations, technological evolution, bureaucratic regulations, logistical challenges, and record-keeping methodologies. Each of these elements not only contributes to our understanding of catapults as military instruments but also reflects the broader context of Byzantine society, where engineering acumen and administrative prowess coalesce to support the empire's military endeavors. While the subject may appear tedious at first glance, delving into the minutiae reveals a complex interplay of factors that shaped one of history's most enduring empires. The dull history of Byzantine imperial catapult calibration and maintenance logs. Part 8: Regional Variations and Comparisons. Within the vast expanse of the Byzantine Empire, a remarkable tapestry of regional variations in catapult calibration and maintenance practices emerged. While the overarching imperial mandate dictated certain baseline standards, the localized adaptations reflected the unique topographical, climatic, and material conditions present in various provinces. In the western provinces, such as Thrace and Macedonia, catapult designs were often influenced by the abundance of local timber sources. The prevalent use of oak, with its dense and resilient characteristics, necessitated a particular calibration method that accounted for the wood's propensity to expand and contract with humidity changes. This led to the establishment of specific humidity gauges and moisture retention tests, meticulously documented in maintenance logs. Comparatively, in the eastern provinces, like Anatolia, where softer woods such as pine were more readily available, catapults were calibrated to account for the reduced tensile strength. As such, the logs from this region often included entries regarding the frequency of recalibrations due to wood fatigue, particularly during the sweltering summers. Moreover, the introduction of local materials, such as the famed volcanic stone from the island of Santorini, prompted further regional distinctions. The logs would frequently note the variance in projectile weight and density, necessitating specific adjustments to the launching mechanisms. In coastal regions, such as those near the Aegean Sea, the calibration logs often reference the influence of sea air on the metal components of catapults, leading to a rigorous regimen of rust prevention techniques that were documented with meticulous precision. Part 9: Evolution over different time periods. As the Byzantine Empire endured the vicissitudes of time, the catapult calibration and maintenance practices evolved in tandem with advancements in technology and shifts in military strategy. During the early Byzantine period, catapults were predominantly simple torsion devices, relying on the elasticity of twisted sinew or hair. The calibration logs from this era predominantly focused on the torque measurements, which were painstakingly calculated by hand, often requiring the full attention of a dedicated scribe. The advent of the Middle Byzantine period saw a marked evolution in catapult design, with the introduction of counterweight mechanisms. This innovation necessitated a corresponding shift in the calibration logs, which began to include detailed calculations of weight distribution and its effect on launch trajectory. Engineers and military tacticians became acutely aware of the need for precision, leading to a proliferation of mathematical formulas that were painstakingly inscribed into the maintenance records. By the late Byzantine period, the introduction of gunpowder and early forms of artillery further transformed the landscape of siege weaponry. The calibration logs transitioned from a focus on physical mechanics to the integration of chemical properties, noting the ratios of gunpowder mixtures and the implications for projectile velocity. This evolution was not merely a matter of technological advancement but mirrored the changing nature of warfare, with logs increasingly reflecting the urgency of adapting to new threats. Part 10: Bureaucratic Regulations and Laws. The Byzantine bureaucracy, with its labyrinthine structure and penchant for regulation, exerted significant influence over the maintenance and calibration of catapults. Imperial edicts, often issued by the emperor or the military strategoi, mandated stringent guidelines regarding the construction, maintenance, and calibration of these weapons. The logs frequently noted compliance with these edicts, often accompanied by references to the specific law or decree cited. For instance, the Novelli of Justinian I, circa 534 AD, included legal stipulations that required regular inspections of siege equipment by designated officials. The logs would chronicle the outcomes of these inspections, including any repairs mandated by the inspecting authority. Such entries often contained bureaucratic jargon that could induce a profound sense of tedium, detailing the exact nature of repairs, the materials used, and the personnel involved in the process. Furthermore, the imperial administration established regulations regarding the training of personnel responsible for catapult maintenance. The logs would reflect the attendance records of these individuals at mandatory workshops, alongside assessments of their proficiency in the calibration techniques. The emergence of a standardized training curriculum resulted in a series of logs that documented not just the equipment but the human resources involved in maintaining the Empire's siege capabilities. Part 11: Supply Chain and Logistics. The supply chain integral to the maintenance of catapults was a complex web of local and imperial resources, carefully documented in the calibration logs. The acquisition of materials such as wood, metal, and cordage was subject to a variety of logistical considerations, including seasonal availability and transportation challenges. The logs would often detail the procurement process, noting the dates of material acquisitions, the sources of supply, and the transportation methods employed. For instance, in the logs from the provinces of Asia Minor, one might find elaborate entries describing the seasonal timber harvests. Detailed accounts would note the specific types of trees felled, the dimensions of the logs, and the estimated yield of usable materials. Additionally, references to the local guilds responsible for crafting these materials were common, including the names of master craftsmen and their apprentices, whose work was critical to the calibration process. The transportation of materials was a significant logistical endeavor, often requiring the coordination of multiple teams of laborers. The logs would meticulously document the routes taken, the number of carts employed, and the duration of the journey. Seasonal changes, such as the onset of winter or harvest periods, were frequently cited as factors influencing transportation efficiency. In some cases, the logs even included commentary on the local fauna that posed threats to material integrity during transit, such as rodents or insects, underscoring the attention to detail that characterized Byzantine logistical practices. Part 12: Record-keeping methods. The record-keeping methods employed in the maintenance and calibration of catapults were as varied as the regions themselves. The Byzantine Empire's penchant for meticulous documentation manifested in a plethora of formats and styles. The primary medium for these records was parchment, with some logs written on wax tablets for temporary entries, later transferred to more permanent forms. The logs often employed a standardized format, beginning with the date of entry, followed by a detailed account of the calibration process undertaken. Entries would typically include the temperature and humidity levels at the time of calibration, as these factors were deemed critical in influencing the performance of the catapults. The use of a scribe was indispensable, with many logs containing annotations in the margins that provided supplementary information or context to the primary entries. In some cases, the logs were supplemented with diagrams illustrating the specific calibration adjustments made, with arrows and notations indicating the desired measurements. These illustrations were often accompanied by mathematical calculations, reflecting the Byzantine commitment to precision. The incorporation of visual aids into the logs served not only as a reference for future calibrations but also as a teaching tool for less experienced operators. Moreover, the logs were often subjected to a system of review and approval, with senior officials required to sign off on entries to ensure compliance with imperial standards. This bureaucratic oversight was meticulously recorded, often resulting in layers of signatures and stamped seals that added a bureaucratic weight to the already detailed entries. In summation, the Byzantine Imperial Catapult Calibration and Maintenance logs represent a remarkable confluence of regional variations, technological evolution, bureaucratic regulation, logistical complexity, and meticulous record-keeping. The expansive detail and mundane nature of these records serve to illuminate the intricate tapestry of Byzantine military engineering, revealing a world where even the slightest deviation in calibration could have profound implications for the empire's military efficacy. It is within this seemingly tedious history that one can find the threads of a civilization grappling with the challenges of warfare, technology, and the relentless march of time. Part 9: Regional Variations and Comparisons in Catapult Calibration. The Byzantine Empire, with its vast expanse stretching from the shores of the Adriatic to the outskirts of the Arabian Peninsula, exhibited significant regional variations in the calibration and maintenance of its formidable catapult systems. Each province, influenced by localized military traditions, available resources, and the unique topographical challenges of its environment, developed its own specific methodologies and standards for catapult operation. For instance, in the mountainous regions of Asia Minor, where the terrain necessitated frequent adjustments in projectile trajectory due to elevation changes, catapult operators adopted a more nuanced approach to calibration. The use of local materials such as timber from the densely forested Pontic Mountains resulted in a unique design of torsion engines. These engines were often outfitted with additional pulleys, allowing for greater adjustments in tension. Conversely, in the flatter plains of Thrace, where distances could be deceptively uniform, calibration protocols favored simplicity and speed. The Thracian catapults were typically of a more standard design, emphasizing rapid deployment and ease of maintenance over complex calibration techniques. The differences extended beyond mere technical specifications. They also reflected the cultural attitudes toward warfare prevalent in each region. In the more militarily aggressive provinces, such as the borderlands of the Danube, catapult calibration logs often included notations on enemy movements and specific tactical adjustments, revealing a proactive approach to siege warfare. In contrast, regions that had experienced prolonged periods of peace, such as parts of the Aegean Islands, recorded less frequent calibrations, focusing instead on routine maintenance and the preservation of equipment in anticipation of potential conflict. Part 10: Evolution over different time periods. The art and science of catapult calibration did not remain static throughout the Byzantine era but evolved considerably over the centuries. Initially, during the early Byzantine period, approximately 330 to 600 CE, catapults were relatively rudimentary in design, relying heavily on the ancient Greek principles of torsion and leverage. Calibration logs from this era, though sparse, indicate that operators primarily focused on adjusting tension and angle based on empirical observations rather than systematic measurements. As the empire entered the Middle Byzantine period, 600–1200 CE, a notable shift occurred. The introduction of more complex designs, such as the onager and the ballista, necessitated a formalization of calibration techniques. The emergence of specialized guilds of catapult operators, known as catapulti, marked a significant development in the professionalization of this craft. Bureaucratic regulations began to dictate the requirements for training and certification, with records showing that master catapult operators were often required to pass stringent tests on both theoretical and practical knowledge of calibration techniques. By the late Byzantine period, 1200 to 1453 CE, the introduction of gunpowder and artillery further transformed the landscape of siege warfare, leading to a decline in the use of traditional catapults. Nevertheless, the meticulous documentation of calibration practices persisted, albeit with a shift towards integrating these logs with artillery maintenance records. The evolution of catapult technology was thus mirrored in the increasingly sophisticated methodologies of record keeping, including standardized formats for logging calibration data. Part 11. Bureaucratic regulations and laws. The Byzantine Empire was renowned for its intricate bureaucratic structures, and the regulation of catapult calibration was no exception. The administration recognized the strategic importance of maintaining a consistent and effective catapult system across its provinces. Consequently, various imperial edicts and local laws were enacted to govern the calibration and maintenance of catapults. One notable regulation was the Practicos Nomos, a comprehensive code that outlined the responsibilities of military engineers and operators. This code mandated regular inspections of catapult equipment and required that calibration logs be submitted to the local military commander on a bi-monthly basis. Failure to comply with these regulations could result in severe penalties, including demotion or even imprisonment for negligence. Furthermore, the empire established a system of inspections by appointed officials known as catapulti, who were responsible for auditing the calibration logs and ensuring that all catapults met the prescribed standards of accuracy. These inspections were often accompanied by a series of tests, wherein catapults would be fired at designated targets, with results meticulously recorded for future reference. The bureaucratic nature of this process often led to redundancy, with multiple layers of oversight that sometimes resulted in discrepancies between logs and actual operational capacity. In addition to military regulations, local governors were empowered to enact additional laws tailored to the specific needs and circumstances of their provinces. These laws could include provisions for emergency repairs in the event of equipment failure or specific protocols for coordinating with local craftsmen who supplied materials for catapult repairs. Part 12. Supply Chain and Logistics. The logistics surrounding the supply chain for catapult parts and materials were as complex as the calibration methods themselves. The Byzantine Empire's extensive trade networks facilitated the procurement of diverse materials necessary for catapult construction and maintenance, including wood, rope, and metal components. Each material's availability often dictated the design and calibration practices employed in different regions. Timber, for instance, was sourced from various locales, with the quality and type of wood impacting both the construction and performance of the catapults. In the forested regions of Asia Minor, robust hardwoods such as oak were favored, while in more arid regions, softer woods like poplar were more readily available but less durable. The supply chain was managed through a network of local artisans and merchants, whose records often included detailed accounts of deliveries and the quality of materials supplied. Rope, an essential component for the torsion mechanisms of catapults, presented its own logistical challenges. The production of high-quality rope depended on a reliable supply of flax or hemp, which varied by region. In coastal areas, where fishing communities thrived, the use of marine fibers was common, while inland provinces relied on agricultural products. The calibration logs occasionally noted the condition of ropes, emphasizing the need for regular replacement and indicating the sources from which they were procured. Lastly, metal components, often used for reinforcing catapults or creating specialized projectiles, had to be carefully managed. The Byzantine Empire's mining operations, particularly in regions such as Thrace and Cyprus, were responsible for supplying the necessary metals, and the transportation of these materials involved meticulous planning. Records of supply routes, including seasonal considerations and potential hazards, were detailed in logistics logs that accompanied calibration data. Part 13, Record-Keeping Methods. The methods of record-keeping employed for catapult calibration and maintenance were as varied and intricate as the practices themselves. Throughout the Byzantine Empire, the documentation process evolved, reflecting changes in technology, bureaucracy, and military doctrine. Early records were often inscribed on wax tablets or parchment, using stylus or ink, respectively. These records consisted of simple entries detailing the date of calibration, the operator's name, and basic adjustments made to the catapult. Over time, as the complexity of catapult systems increased, so too did the sophistication of record-keeping methods. By the Middle Byzantine period, standardized forms emerged, allowing for more detailed entries that included specific measurements of tension, angle, and even environmental conditions, such as wind speed and humidity, at the time of calibration. The introduction of parchment scrolls offered a more durable medium for record-keeping. These scrolls often contained not only calibration logs but also historical anecdotes, tactical notes, and even illustrated diagrams of catapult designs. The practice of maintaining illustrated records was particularly prevalent in regions with a strong tradition of military engineering, where visual aids were deemed essential for training new operators. By the late Byzantine period, as literacy rates increased and bureaucratic oversight expanded, the use of bound codices became more common. These codices contained systematic entries, often organized by date and region, allowing for easier cross-referencing and analysis. The meticulous nature of these records played a crucial role in the empire's military strategy, as commanders could review historical calibration data to inform decisions on troop deployment and siege tactics. In conclusion, the history of catapult calibration and maintenance within the Byzantine Empire is a reflection of the broader complexities of military logistics, regional diversity, and bureaucratic regulation. As the empire evolved, so too did the practices surrounding these formidable siege engines. The detailed logs, regulations, and methodologies developed over centuries not only underscore the significance of catapults in Byzantine warfare but also illuminate the intricate interplay between technology, culture, and governance. Thus, the saga of Byzantine imperial catapult calibration and maintenance logs continues to serve as a testament to the diligent efforts of those who toiled in the shadows of history, ensuring the efficacy of a vital component of their military prowess. The Dull History of Byzantine Imperial Catapult Calibration and Maintenance Logs, Part 10. The intricacies of Byzantine imperial catapult calibration and maintenance logs extend beyond mere technical specifications and operational procedures, branching into regional variations and comparisons that reveal the diverse practices adopted across the empire. As the Byzantine Empire stretched from the fringes of Italy to the vast reaches of Anatolia and beyond, regional adaptations in the calibration and maintenance of catapults were inevitable. These regional differences were influenced by local resources, climatic conditions, and the tactical necessities arising from specific military challenges. In the Western territories, particularly in the provinces of Thrace and Macedonia, where the rugged terrain presented unique challenges, catapults were often calibrated to accommodate the varied altitudes. The logs from these regions reflect meticulous adjustments made to the tension of the torsion springs, taking into account the density of the air and the elevation of the launch site. These adjustments, noted in the maintenance logs, included detailed accounts of the types of wood used for the frame and the ropes, which varied from region to region due to availability. The Thracian logs, for example, often detail a preference for locally sourced beech wood, prized for its durability and elastic properties, while the logs from the more arid regions of Anatolia frequently cite the use of juniper for its resistance to warping in dry conditions. Conversely, in the coastal provinces like Asia Minor, the logs reflected an emphasis on corrosion resistance, as salt from the sea air presented a significant challenge to the longevity of metal components. The maintenance logs from these regions documented the application of various natural oils and resins to protect metal parts, with a notable mention of olive oil mixtures, which were found to be effective in repelling moisture. As the Byzantine Empire evolved over different time periods, so too did the methodologies employed in catapult calibration and maintenance. The transition from the early Byzantine period, where catapults were primarily rudimentary and based on ancient Greek designs, to the more sophisticated models of the late Byzantine period highlights an evolution in not only technology but also in the bureaucracy surrounding these weapons. The logs from the early era, often handwritten and somewhat haphazard in nature, contrast sharply with the later, more standardized entries that include precise measurements, diagrams, and even the names of the officials responsible for each calibration. One notable period of transition occurred during the reign of Emperor Alexios I Komnenos, 1081 to 1118, when the logistical demands of the Byzantine military were heightened due to the encroachment of the Seljuk Turks. This period saw the establishment of more formalized bureaucratic regulations surrounding the production and maintenance of siege engines. The logs from this time reflect a greater emphasis on accountability, with entries meticulously detailing the quantity of timber and metal required for repairs, the labor hours logged by craftsmen, and the specific dates of inspection. These regulations were likely codified into a formal decree, which specified the standards that all provincial governors were required to follow, thereby creating a semblance of uniformity across the empire. The bureaucratic regulations and laws governing catapult calibration and maintenance were not merely administrative formalities but rather reflections of the Byzantine Empire's intricate governance system. Various edicts issued by emperors, such as the Prochiron and the Ecloga, contain stipulations regarding the maintenance of military equipment, including siege engines. These legal frameworks ensured that catapults were not only maintained in good working order but also that the responsibility for their upkeep was clearly delineated among local military commanders and artisans. The supply chain and logistics involved in the maintenance of catapults were equally complex. The logs often document the procurement processes for materials, which could involve intricate negotiations with local suppliers or even the requisitioning of resources from neighboring provinces. The transportation of heavy materials, such as timber and iron, required careful planning. Detailed entries in the maintenance logs provide insights into the routes taken by transport caravans, often highlighting the challenges posed by rough terrain or hostile territories. For instance, logs from the eastern provinces might include accounts of delays caused by bandit activity along trade routes, necessitating additional military escorts to ensure the safe delivery of vital resources. Moreover, the Byzantine Empire's intricate web of trade networks allowed for the movement of specialized materials across vast distances. The logs sometimes reflect the importation of rare wood types from distant lands, such as the famed cedar from Lebanon, which was sought for its light weight and strength. The careful documentation of these transactions underscores the importance placed on quality materials for the construction and maintenance of effective siege engines. Record-keeping methods employed in the logging of catapult calibration and maintenance further illuminate the Byzantine approach to military logistics. The advent of standardized forms and templates for recording maintenance activities can be traced back to the late 10th century, as the empire began to develop a more bureaucratic system of governance. These records, often maintained by a designated log keeper, included various columns for date, type of maintenance performed, materials used, and the names of the individuals involved in the process. It was common for the log keepers to use a system of abbreviations and symbols to denote specific actions, which would later require translation by higher-ranking officials during audits. The importance of accuracy in record-keeping cannot be overstated. Discrepancies in logs could lead to accusations of negligence or mismanagement, prompting investigations by imperial officials. The logs would often be reviewed during periodic inspections, and it was not uncommon for the emperor himself to take an interest in the state of the empire's siege engines, particularly during times of heightened military activity. The logs thus served not only as maintenance records but also as a reflection of the state of military readiness, providing a historical account of the empire's strategic capabilities. Additionally, the transition from scrolls to codices marked a significant evolution in the manner of documentation. The shift to codex format allowed for easier referencing and cross-referencing of related entries, which proved invaluable during military campaigns when quick access to calibration logs was necessary. The codices were often bound in leather and housed in the military arsenals, where they were protected from the elements. As we delve deeper into the annals of Byzantine catapult calibration and maintenance logs, one cannot overlook the tangential information surrounding related topics that further enrich our understanding of this seemingly mundane subject. The study of siege engines, for instance, invites a broader examination of the artistry and engineering prowess characteristic of the Byzantine military. The logs frequently mention notable artisans whose expertise in constructing and maintaining catapults was widely recognized, many of whom were celebrated in the local communities. Moreover, the socio-political ramifications of catapult use extended beyond mere military applications. They were also a means of psychological warfare. The logs occasionally reflect on the morale of troops and the reputational impact of successful or failed sieges, indicating a keen awareness of the broader implications of catapult deployment on imperial prestige. In conclusion, the Byzantine imperial catapult calibration and maintenance logs reveal a rich tapestry of regional variations, bureaucratic regulations, supply chain logistics, and meticulous record-keeping that together portray a complex and often overlooked aspect of the Byzantine military apparatus. While the mundane nature of these logs may seem tedious, they serve as a vital historical resource, illuminating the intricate interplay between technology, governance, and military strategy in one of history's most enduring empires. The continuous evolution of practices and regulations surrounding catapult maintenance reflects not only the technological advancements of the time but also the adaptive nature of the Byzantine Empire in response to both internal and external challenges. Thus, as we continue to sift through the extensive documentation of catapult calibration and maintenance, we are reminded of the often ignored yet vital role that these logs played in the larger narrative of Byzantine military history, a narrative rich in detail, complexity, and the quiet diligence of those tasked with the mechanical upkeep of an empire's formidable war machines. The subject of Byzantine imperial catapult calibration and maintenance logs might seem, at first glance, to be an esoteric niche carved out in the annals of history. However, as we delve deeper into the minutiae of this subject, we unearth a trove of information that not only captures the imagination but also underscores the rich tapestry of Byzantine military engineering and administrative practices. In this extensive analysis, we shall explore a variety of aspects related to this topic, including minor historical figures involved in the calibration and maintenance of catapults, specific case studies with dates, comparative analysis with other regions, and archaeological findings that provide a more profound understanding of these ancient machines. Minor historical figures and their roles. While many well-known figures such as Emperor Justinian and the military engineer Procopius dominate the narratives around Byzantine warfare, several lesser-known individuals played crucial roles in the development and maintenance of catapult technology. One such figure is Anastasios the Mechanic, a lesser-known engineer during the reign of Emperor Maurice, 582 to 602 AD. Anastasios is documented in a series of maintenance logs, where he outlined the calibration processes of the empire's catapults in detail, particularly focusing on the tension adjustments required for optimal performance. His logs contain meticulous notes on the types of wood suitable for the construction of torsion springs, as well as weather conditions influencing elasticity. For instance, he noted, in the month of Hecatombeon, the ash wood tends to swell and lose its tensile strength. Therefore, it is wise to replace the springs within this period. Such details reflect the precision with which these machines were treated and underscore the importance of individuals like Anastasios in the Byzantine military apparatus. Another figure of note is the log keeper Ioannis, who served under Emperor Alexios I Komnenos, 1081 to 1118 AD. His records, although sparse, provide insight into the logistical challenges faced in maintaining catapults during the First Crusade. In his writings, Ioannis lamented the difficulty of transporting heavy catapults across the rugged terrain of Anatolia, stating, "The path to the citadel of Nicaea is fraught with obstacles, and our catapults, though fearsome in stature, are but burdens to our weary men." His observations shed light on the operational challenges of Byzantine war machines, emphasizing both the strategic utility and practical limitations of catapults in warfare. Specific case studies with dates. To illustrate the application of catapult calibration and maintenance logs in a historical context, we can examine the Siege of Antioch in 1098. During this period, Byzantine forces collaborated with the Crusaders to besiege the city, and catapults played a pivotal role. The logs from a certain engineer named Eudoxios reveal that meticulous calibration was essential for the siege's success. On May 15, 1098, Eudoxios recorded, after adjusting the angle of elevation to 35 degrees, we achieved a range of 300 paces, striking the city walls with great efficacy. This detail underscores the importance of precise calibration in warfare. The logs also detail the maintenance of the catapults, noting the replacement of worn-out ropes and the need for regular inspections. On June 1, 1098, he wrote, "The torsion springs have lost elasticity, 2 sets have been replaced. It is imperative that we keep our siege engines in peak condition, lest they fail us in our hour of need." Another notable case study is the Siege of Thessalonica in 1185, where Byzantine catapults were employed against the Normans. The logs maintained by the chief engineer, Georgios, document the emotional and physical toll of operating these machines. On July 10, Georgios lamented, "The men grow weary, and the wood of our catapults, though strong, begins to splinter from the relentless strain. We must recalibrate before the next assault." This case study not only highlights the technical aspects of catapult operation but also offers a glimpse into the human experience behind these monumental machines. Comparative analysis with other regions. When comparing Byzantine catapult technology to that of other regions, particularly the Islamic world and Western Europe, distinct differences emerge in both design and operational philosophy. Byzantine engineers, influenced by Greek and Roman traditions, often utilized torsion-powered catapults known as ballistae, which were capable of launching large projectiles with remarkable accuracy. In contrast, contemporary Islamic siege engines, such as the mangonel, employed a different mechanism based on a swinging arm, which allowed for a broader arc of fire but often at the cost of accuracy. The maintenance logs of the Byzantine catapults reveal an emphasis on meticulous calibration, often documented with specific measurements and observations regarding materials and weather conditions. For example, a log from the year 1230 highlights the calibration practices employed during the Siege of Constantinople, noting, "The humidity has caused the wood to swell, we must account for this in our tension settings. In contrast, the Islamic engineers, as recorded by historians such as Al-Ma'mun, focused more on the rapid assembly and deployment of siege engines rather than detailed maintenance logs. Al-Ma'mun's writings suggest a more improvisational approach, stating, "In the heat of battle, the swift construction of a mangonel is often favored over meticulous calibration. Let the winds guide our aim." Similarly, Western European catapults, particularly during the medieval period, also prioritized speed and mobility over precision. The logs of English engineers during the siege of Rochester in 1215 reveal a much simpler approach, stating, "The catapults are to be erected hastily. We shall trust in the will of God for accuracy." This comparative analysis highlights the Byzantine emphasis on precision and documentation, setting them apart from their contemporaries. Archaeological findings and interpretations. In recent decades, archaeological excavations at various Byzantine sites have revealed tangible remnants of catapults and their components, providing further insights into the calibration and maintenance practices of the time. One significant find occurred at the site of Dyrrhachium, where researchers unearthed a series of catapult fragments alongside a trove of logs documenting their maintenance schedules. The remnants of torsion springs and wooden frames have allowed historians to reconstruct the operational capabilities of these machines. One notable interpretation from these findings comes from Dr. Helena Papadopoulos, who posits that the wear patterns on the wood suggest a rigorous maintenance regime. The evidence indicates that these catapults were not only used extensively but were also maintained with a level of care that reflects the Byzantine commitment to military efficacy, she noted during a lecture at the Byzantine Studies Conference in 2022. Such archaeological evidence complements the written logs and offers a multidimensional understanding of catapult technology. Another significant site is the Fortress of Mistras, where a cache of catapult ammunition was discovered. The examination of these projectiles has led to revelations about the types of materials used in their construction. Dr. Nikos Stavros remarked, "The variety of stones indicates that the Byzantines were not averse to experimenting with different projectiles, adapting their strategies based on available resources." This adaptability, as evidenced by both the logs and archaeological findings, points to a sophisticated understanding of both engineering and logistics within the Byzantine military. Primary source quotations, invented but plausible. To further ground our analysis in the written record, we can introduce plausible but invented primary source quotations from the logs and letters of Byzantine engineers and military officials. These quotations can provide a sense of authenticity and immerse readers in the historical context of catapult calibration and maintenance. From the log of Anastasios the mechanic, we might find the following entry. On the eve of the festival of the Theotokos, I recorded that the catapults must be inspected, for if they falter, the wrath of our enemies shall surely rain upon us. This fictional entry reflects the blend of religious and military imperatives that characterized Byzantine life. In another entry from the logs of Eudoxios, dated June 15, 1098, he wrote, "As the sun rises over the besieged walls of Antioch, our spirits lift with the knowledge that our catapults, newly calibrated, stand ready to hurl forth the might of the empire." This quote encapsulates the interplay between technology and morale in the Byzantine military. Finally, from the correspondence of Georgios, we might read, "The splinters of wood and the cries of our men remind me that the art of war is as much about maintenance as it is about the thrust of projectiles. Let us ensure that our catapults sing true." Such quotations help to humanize the engineers and soldiers, framing them within the broader narrative of Byzantine military history. In conclusion, the Byzantine imperial catapult calibration and maintenance logs serve as a fascinating window into the complexities of military engineering, logistics, and everyday life in the Byzantine Empire. Through the exploration of minor historical figures, specific case studies, comparative analyses, archaeological findings, and invented primary sources, we can appreciate the depth of detail that characterized this seemingly mundane aspect of history. The careful calibration and maintenance of catapults were not merely technical concerns but intertwined with the very fabric of Byzantine military strategy and identity. Thus, as we delve deeper into the dull history of Byzantine imperial catapult calibration and maintenance logs, we come to realize that even the most seemingly tedious subjects can yield profound insights into the human experience. As we close, let it be noted that the legacy of these logs, while perhaps not as glamorous as the grand battles fought with these machines, provides a unique glimpse into the meticulousness and dedication that characterized the Byzantine approach to warfare. In an age where technology was entwined with the fate of empires, such attention to detail was not just prudent, it was essential for survival amidst the chaos of conflict. The history of Byzantine imperial catapult calibration and maintenance logs, while often overshadowed by more glamorous aspects of Byzantine military history, is marked by a succession of minor yet pivotal figures whose contributions shaped the nature of siege warfare and artillery technology. The meticulous documentation of these logs provides an invaluable insight into the Byzantine Empire's military logistics and engineering practices, although the narrative itself might seem tedious to the modern reader. #### minor historical figures in Byzantine catapult development. One such minor historical figure is Leo the mathematician, who, though not a household name, played a crucial role in the advancement of artillery technology in the 9th century. His treatises on mechanics, particularly in the realm of siege engines, laid the groundwork for the calibration of various catapults used during the Byzantine campaigns. His works, often referred to by their Latinized title De Machinis, discuss the principles of leverage and projectile motion, albeit in a manner that could induce yawns in even the most enthusiastic of scholars. Leo's contemporaneous log entries, preserved in several dusty manuscripts, reveal the specific dimensions and weights of projectiles used in various engagements, such as the notable siege of Sardis in 878 AD. His meticulous notes on the ratio of the arm length to the weight of the counterbalance highlight an early understanding of mechanical advantage, yet the dry prose has led many historians to overlook the significance of these contributions. Another notable figure is Michael of Ephesus, a lesser-known engineer and inventor active in the 12th century. His maintenance logs, which he kept while overseeing the construction of catapults near the walls of Constantinople, provide a window into the daily operations of siege machinery. The logs include exhaustive details on the replacement of torsion springs and adjustments to the tension ropes used in the catapults, often accompanied by laborious calculations that would make even the most seasoned engineer's eyes glaze over. One illustrative entry from 1135 notes, on the third day of the month of May, the wooden yoke was found to be a span too short, necessitating the addition of a new piece, 1.5 cubits in length, thus ensuring optimal projectile release angle. ### Specific case studies of Byzantine catapults. Examining specific case studies can illuminate the practical applications of these logs, albeit in a rather monotonous manner. The 1204 siege of Constantinople during the Fourth Crusade provides an intriguing, albeit tedious, tableau for the analysis of catapult use. The logs from this period reveal that the Byzantines employed a variety of siege engines, including large stone-throwing catapults known as onagers, which were calibrated to launch projectiles weighing upwards of 100 kilograms. The logs indicate a systematic approach to calibration, detailing the precise angle of elevation required to ensure maximum range. An entry from the summer of 1203 states, the angle of elevation was set at 45 degrees, with adjustments made to the counterweight, yielding a launch velocity of precisely 15 meters per second. Such entries, while lacking in dramatic flair, underline the Byzantine focus on precision in warfare. ### Comparative analysis with other regions. The Byzantine approach to catapult calibration and maintenance can be juxtaposed with that of their contemporaries, particularly the Western European powers and the Islamic states. While the Byzantines were renowned for their engineering precision, their Western counterparts often relied on brute force and sheer numbers rather than meticulous calibration. For instance, the trebuchet, a later innovation popularized in France, operated on different principles and did not require the same level of mechanical knowledge regarding torsion ratios, making it less precise but more straightforward to construct and operate. The Arabic treatises on siege warfare, such as those by al-Jazari, also highlight a divergence in methodology. Al-Jazari's logs from the 12th century emphasize the use of water-powered mechanisms for launching projectiles, showcasing an alternative approach to catapult design. While the Byzantines focused on the tension of ropes and the weight of counterbalances, the Islamic engineers pursued hydraulic solutions, which, in theory, could provide greater power with less mechanical complexity. However, Byzantine logs clearly indicate a consistent effort to refine and enhance existing technologies rather than adopting radically different methods. ### Archaeological findings and interpretations. Archaeological excavations at sites such as Dara and Amida have revealed remnants of catapults and their maintenance logs inscribed on clay tablets. These findings, while fascinating to a select audience, often provoke more yawns than excitement among the general populace. The catapult remnants, including fragments of torsion springs and wooden frames, have been carbon dated to the 6th century and correlate with entries in maintenance records that describe repairs and replacements over time. One significant find near Constantinople in 1967 involved the discovery of a catapult mechanism that had been buried beneath layers of sediment. The accompanying log entries, discovered in the ruins of a nearby military workshop, detailed the materials used and the processes of calibration. An entry dated to 610 AD states, "The wood from the oak of the forest near Nicaea proved to be most effective in the construction of the catapult arm, as it provides the necessary elasticity without compromising integrity." Such statements, while methodical, are emblematic of the dry documentation style that characterizes much of the Byzantine record-keeping. #### primary source quotations. To further immerse the reader in the dullness of Byzantine catapult history, let us imagine plausible primary source quotations that might have been found in the logs. One entry might read, "On the 15th day of the month of September, the tension of the ropes was measured thrice to ensure optimal performance, and it was found that a tension of 50 units provided optimal projectile acceleration." Another could state, "The diameter of the stone projectiles was recorded as 10 inches, with the weight being precisely 75 pounds, leading to an expected launch distance of 300 paces, barring any unforeseen wind resistance." Such quotations serve to illustrate the level of detail that Byzantine engineers committed to their logs, yet they also highlight the tedium of this historical narrative. The relentless focus on measurements and precise calculations underscores a culture deeply entrenched in the mechanics of warfare, albeit one that may not captivate the imagination. ###conclusion. In conclusion, the history of Byzantine imperial catapult calibration and maintenance logs is a tapestry woven with the threads of minor historical figures, specific case studies, comparative analyses, archaeological findings, and primary source quotations that, while exhaustive, may ultimately induce sleep rather than excitement. The meticulous nature of the logs reflects a society dedicated to precision in military engineering, yet the sheer volume of data and the lack of dramatic flair render this history a rather monotonous account. The Byzantine Empire's catapult calibration practices offer a window into the logistical frameworks that underpin their military endeavors, yet the intricate details, while important for understanding the empire's technological advancements, may leave the modern reader longing for a more thrilling account of history. The focus on mechanical specifications, numerical measurements, and procedural documentation serves as a reminder of the often overlooked aspects of warfare that are essential for comprehending the broader narrative of the Byzantine military machine. Thus, as one delves into the depths of the Byzantine logs, one must brace for a journey through a landscape populated by numbers, ratios, and specifications, where the excitement of siege warfare is overshadowed by the tireless documentation of its mechanical underpinnings. And so, as the pages turn, one might find themselves lulled into a state of tranquility, succumbing to the hypnotic rhythm of a history that, while significant, is undeniably dull. And so, dear listeners, we come to the end of our gentle journey through the fascinating yet often overlooked realm of Byzantine imperial catapult calibration and maintenance logs. As we've explored the meticulous records kept by the dedicated artisans and engineers of a bygone era, we've uncovered not just the details of their work, but also the dedication and precision that went into every launch and adjustment. From the intricate designs of the catapults to the careful notations of their upkeep, we've seen how these historical instruments of siege warfare were not just tools of destruction, but also marvels of engineering that required a delicate balance of skill and knowledge. The logs tell a story of careful planning, the importance of accuracy, and the relentless pursuit of improvement, qualities that transcend time and resonate with us even today. As you lay your head down tonight, may the echoes of these ancient practices lull you into a restful sleep. Imagine the rhythmic sound of the logbooks quill scratching against the parchment, each stroke a reminder of the diligence and care that went into the craft. The soft whispers of history can provide comfort, much like a gentle breeze rustling through the leaves on a warm summer evening. Remember, dear listener, if the soothing cadence of our narrative still lingers in your mind, you are welcome to replay this journey whenever you wish. Let the calmness of the Byzantine era wrap around you like a warm blanket, inviting you to drift deeper into tranquility. The stories of the past can be a source of serenity, guiding you to a place of peace as you surrender to the embrace of sleep. So, as you close your eyes, may your dreams be filled with the warm glow of candlelight illuminating the pages of history, the soft thud of catapults launching into the night sky, and the gentle sighs of those who meticulously maintain them. Allow the weight of the day to melt away, replaced by a sense of calm and the promise of rejuvenation that comes with a good night's rest. Thank you for joining me on this soothing expedition through time. May the peace of the night cradle you, and may you awaken refreshed and inspired by the beauty of both history and dreams. Sleep well, dear listeners, and good night.